In this video, we will look at the factors that affect the rate of SN1 reaction. The first thing we are going to see is how the substituent affects the rate of the SN1 reaction. Now we are aware that the rate determining step, the rate determining step of the SN1 reaction depends on the formation of carbocation. Since tertiary carbocation, since the order of stability of carbocations depends on the following, like tertiary carbocations are much stabler than secondary, which are much stabler than primary, which are much stabler than methyl. And hence, a carbocations, we can write this as CH3 plus. Hence, the order or the ease with which or the SN1 reactivity is also for the SN1 reactivity also follows the same order. That is, a tertiary alkyl halide, a tertiary alkyl halide will react faster than a secondary alkyl halide. A tertiary alkyl halide will react faster than a secondary alkyl halide, which would react faster than a primary alkyl halide, which would react faster than a methyl alkyl halide. So this is the rate at which the rate depends strongly on the stability of carbocations. Now, the reason why tertiary carbocations are very stable is due to two effects. One is so tertiary carbocations are stable because of two reasons. One is the inductive effect, and another one is the inductive effect, and another one is the due to hyperconjugation. The second reason is the leaving group effect. Leaving group effect. Now here, so when in an SN1 mechanism, let's say these are the three alkyl groups. This X has to depart. So this X has to depart for the formation of the carbocation. So for the formation of carbocation. And this X will leave, should be a very good leaving group, should be a very good leaving group. And this is possible when, when X minus is a conjugate base of a strong acid. So when X is a, say for example, Cl minus, its conjugate base is, its conjugate acid is, so Cl minus is the conjugate base of a strong acid. So since it's the Cl minus is the conjugate base of a very strong acid, Cl minus is a good leaving group. Since Cl minus is a good leaving group, the formation of, so since it's a good leaving group, the formation of carbocations is accelerated. The third factor that influences the SN1 reaction is the sol depends on the type of solvent one uses. So let's call it as the solvent effects. And what we observe is that the SN1 reaction goes much more rapidly in polar solvents that stabilizes the ion. So SN1 reaction is much faster in a polar solvents that stabilizes the ions. So alcohol and water are two good examples of, say for example, alcohol or water or methanol, that is an alcohol, are two good examples of polar protic solvents. So there are two examples of polar protic solvents. And how do they help in accelerating the SN1 reaction? Now, polar solvents such as alcohol, that is methanol, and water, what do they do is they form hydrogen bonds with the anion, that is the leaving group, with the anion, that is the leaving group, and also with the cation, which is the carbocation in this case. So they are in, by solvating these ions, they help to stabilize them, and they help to polarize the Rx bond. We can see this as that for the formation of carbocation, the bond between the carbon and the halogen has to be broken, and this happens more easily if we are able to stabilize the carbocation and the uh, anion, that is the leaving group, and this is possible when we use a polar protic solvent which stabilizes these ions by solvating them. So an SN1 reaction goes much more rapidly in polar solvents that stabilizes the ions.